You've likely heard the old adage, breakfast like a king, lunch like a prince, and dinner like a pauper. But does this notion have scientific merit? Today, we take a look at how having dinner at 2 p.m. can boost fat burning capacity, reduce appetite, and even enhance metabolic flexibility. Welcome to the HVMN Research Roundup, a series where we explore some of the most interesting and newest studies in nutrition, metabolism, and human performance. I'm here to walk you through these studies and share my thoughts and insights along the way. Our regulars know that one of our channel's key focus areas is intermittent fasting and how to apply it for health and human optimization. However, fasting can be made complicated because there's so many variations of how to fast. There's 16-8, OMAD or 1 meal a day, 36-hour monk fast, and extended 3 to 7 day water fast. Basically, any pattern that increases the pause of eating versus the constant eating and grazing prevalent in modern culture can be considered to be some form of intermittent fasting. Time-restricted feeding, or TRF, is one term commonly used in scientific literature. This feeding is not restricted by types of food more than types of macronutrients, but is restricted by time. A variation of time-restricted feeding is early time-restricted feeding, or ETRF. ETRF is what we'll be discussing today, so I'll be using this acronym a lot. ETRF differs from other TRF regimens by shifting the majority of food consumption to earlier in the day. A lot of people with fasting regimens skip breakfast and have a late time-restricted feeding window. For example, a late lunch and a dinner, say 2 p.m. lunch and a 7 p.m. dinner. This is the pattern I actually very often use. But with ETRF, the fasting window starts and ends earlier. For example, 8 a.m. start and a 2 p.m. end, therefore a 2 p.m. dinner. Well, why could ETRF be better than other time-restricted feeding protocols? There are several theories, but one of the best contenders revolves around circadian rhythm. In short, circadian rhythms are the sunrise and sunset clocks present in our cells. Nearly every organ in our body operates on some circadian rhythm. Throughout the day, changes in gene expression determine how we feel, how we perform, and how our body metabolizes energy. In particular here, we observe that insulin and other metabolic processes tend to peak earlier in the day. This begs the question that perhaps shifting food intake to earlier in the day, when metabolism is more geared to the task, may improve metabolic control. Some research has shown that eating a large breakfast and a smaller dinner leads to a decrease in appetite and food intake. Other data suggests that restricting the window of eating to an earlier window can increase the body's energy expenditure. In contrast to the benefits of proper meal timing, studies also support the consequences that eating out of sync with circadian rhythms, for example, munchies late at night, promotes weight gain and metabolic dysfunction. So given all this smoke and evidence, the adage to eat breakfast like a king might be a good one. However, the specific mechanisms as to why early time-restricted feeding might be more beneficial than other meal timing interventions, or even the standard way of eating, is unclear. Is it through appetite? Is it through metabolic hormones? Is it through energy expenditure or metabolic flexibility, or something else that gets the credit for the benefits of ETRF? A new study sought to help answer this question. The study, titled Early Time-Restricted Feeding Reduces Appetite and Increases Fat Oxidation but does not affect energy expenditure in humans, was published in July 2019 in the scientific journal Obesity. This study was the first randomized controlled trial to investigate whether meal timing has an influence on energy expenditure and other factors important for weight loss. The researchers hypothesized that early time-restricted feeding would increase 24-hour energy expenditure and other metabolic variables when compared to a meal schedule that resembled the typical American pattern of eating. Let's go over the experiment structure. The two eating pattern studies were this. 1, an ETRF protocol of 6-hour eating window, with meals eaten at 8 a.m., 11 a.m., and 2 p.m., versus the standard American eating pattern of a 12-hour eating window, with meals at 8 a.m., 2 p.m., and 8 p.m. Each of these patterns was done for 4 days. This study was a randomized crossover study, which means that the order in which the participants would receive the two eating patterns would be determined by chance, but each person would eventually do both patterns. So we're really comparing an 18-hour fasting window versus a 12-hour fasting window over a period of 4 days. After participants finished the first eating pattern, there was a washout period of 3.5 to 5 weeks where everyone ate their usual pattern before returning and starting the other alternate diet. On days 1 and 2 of each pattern, participants were studied in free living conditions, meaning that they didn't report into the lab and were told to eat their meals at home, while still complying to their meal timing schedule. On days 3 and 4, all study meals were provided to the participants and eaten in the lab under supervision. Dietary composition was 50% carbohydrate, 35% fat, and 15% protein. But this was only validated for the meals that each participant was provided, not what they ate on their own at home. Day 4, the last day, was the big day. Participants were studied for 24 hours inside of a respiratory chamber, basically a room-sized box that gathers information about participants' metabolism using a technique known as indirect calorimetry. This measures how much carbon dioxide is produced and how much oxygen is consumed by sampling the air that is expired, which can then be used to determine things like energy expenditure, energy consumption, and substrate oxidation, or the different metabolic fuels someone is using. While inside the chamber, everyone was given 3 identical meals at times that corresponded to the particular pattern they were in at the time. So for example, the 8 a.m., 11 a.m., and 2 p.m. for the eTRF group, and the 8 a.m., 2 p.m., and 8 p.m. for the control group. This was simply a meal of strawberry yogurt smoothie with whey protein, skim milk, along with a peanut butter and jelly sandwich. Obviously, this wasn't designed for maximal nutritional density, but mainly just to enable measurement of post-meal energy expenditure and metabolism, which is measured in between 60 and 85 minutes following each meal. The chamber also measures something called metabolic flexibility. This is a hot buzzword that you've probably heard me reference before. And metabolic flexibility refers to the body's ability to switch between oxidizing different substrates, basically fat and carbohydrate. Someone who is metabolically flexible might increase their reliance on glucose after a high-carb meal since they're insulin sensitive and ready to burn carbohydrate, but at the same time, they also have a very high ability to utilize fat. Along with the measures of energy expenditure and substrate oxidation inside the chamber, the study measures several other biomarkers like blood levels of hunger-related hormones, ghrelin, leptin, peptide YY, and glucagon-like peptide. Throughout the study, participants were also asked about the appetite, energy, and asked to rate things like hunger, desire to eat, and capacity to eat, fullness, stomach fullness, energy levels, awakeness, and perceived body temperature. Now that we have the experimental structure set, let's dig into the results. A total of 11 people completed the study, 7 men and 4 women. On average, they were 32 years old and had a BMI of 30. First, let's talk about energy expenditure. The overarching finding here was that early TRF did not influence total 24-hour energy expenditure compared to the control pattern. Therefore, there was no difference in weight loss between the 2 different groups. However, energy expenditure did fluctuate during the feeding and fasting windows. eTRF increased energy expenditure during the daytime, where participants burned 56 extra calories versus the control. However, this was also accompanied by a lower energy expenditure at night, where eTRF participants resulted in 46 fewer calories burned compared to control. Therefore, overall energy expenditure during the overall 24-hour period basically evened out. However, eTRF did seem to increase the thermic effect of food after meals. The thermic effect of food was higher after the second and third meals of the day in the eTRF group compared to the control pattern. This was probably one of the reasons for the higher energy expenditure during the day in the early TRF group. Again, while energy expenditure was higher at these specific times of the day, there was no overall difference when you averaged it out over the 24-hour period. Let's look at metabolic flexibility, which is an important variable and factor for human health and performance. In this study, fuel utilization was measured using non-protein respiratory quotient, or RQ. And this RQ measures the ratio of volume of carbon dioxide expelled versus oxygen consumed. A ratio of 0.7 means 100% fat oxidation. A ratio of 1.0 means 100% carbohydrate oxidation. The difference between the largest and smallest value of RQ is a good marker and a good metric to measure metabolic flexibility. The greater the difference, the better the metabolic flexibility. eTRF led to a reduced 24-hour RQ, which indicates that participants were oxidizing more fat for fuel during the eTRF regimen compared to control. The main differences in RQ were observed between 8 p.m. and 8:30 a.m., which makes sense because this period of time is when all these participants were well into their fasting period. There was a larger, statistically significant difference between the highest and lowest value of RQ over the 24-hour period that it was measured. There was also several significant differences in the metabolic hormones between the two groups. Those following the ETRF pattern had lower levels of ghrelin, leptin, and glucagon-like peptide. In the evening, ghrelin was also reduced, while a hormone known as peptide YY increased. When morning and evening values were averaged, the ETRF regimen lowered levels of ghrelin and tended to increase levels of leptin, while no changes were seen in the control group. But how did the participants actually feel through the study? And this is potentially the most important factor given a dietary protocol. Early time-restricted feeding decreased several measures of appetites in the middle of the day. For example, participants on ETRF reported lower subjective ratings for the desire to eat, while increasing their ratings of fullness during the day. All this is to suggest that restricting the feeding window and extending the fasting period didn't adversely affect hunger or make participants any more hungry than usual, which would have been reflected in increased hunger and decreased satiety throughout the day and night. Now that I highlighted the key results, let's dig into the analysis and my thoughts here. The study did find that ETRF in a 4-day period influenced and improved fat metabolism and improved metabolic flexibility. Even when no differences in energy expenditure were observed, ETRF resulted in enhanced fat oxidation over a 24 period. And this was indicated by the low respiratory quotient. This finding makes a lot of sense, given that the participants in ETRF had a substantially longer fasting period compared to the control group, 18 hours compared to 12. We know that fasting for even a moderate duration leads to increased fat oxidation and a lower reliance on carbohydrates for energy. This study confirms that and indicates that especially throughout the night, ETRF enhances your fat burning capacity. Another cool result is that enhanced metabolic flexibility in the ETRF group is suggestive that this pattern might be better at teaching the body to efficiently use different energy substrates in response to supply and demand. During the day, the ETRF group had a respiratory quotient that indicated a mix of carbs and fat being burned for energy. And this makes sense because these people were in a fed state between 8 a.m. and 2 p.m. However, as the fasting period started kicking in, the RQ in this group steadily declined as fasting kicked in and people started going through the night without additional fuel. And therefore, the RQ gets lower and lower. And that's a really cool result because improved metabolic flexibility is an important aspect for preventing and treating metabolic conditions like type 2 diabetes and obesity, as well as an important aspect for peak human health and performance. A common argument against intermittent fasting is that it will increase your hunger, making the strategy unfeasible or unbearable for most people. This study provided evidence that desire to eat was actually reduced through the day and fullness increased in the ETRF group. The appetite regulation might have something to do with the reduced levels of ghrelin in the morning, and again, ghrelin is known as a hunger hormone, and lower levels would indicate a lower desire to eat. Furthermore, peptide YY, a hormone indicating satiety, was increased in the middle of the day. So each of these changes in hormone levels likely contributed to the overall beneficial lack of hunger experienced by the ETRF group. This was a nice study, but we should call out its limitations and provide broader context given my experience and the community's experience around fasting, ketogenic diets, and all sorts of intervention relating to metabolism and metabolic flexibility. First of all, this was a small study with just 11 subjects, with this pool somewhat skewed towards men. Larger N, of course, will help affirm the generalizability of the ETRF approach. Secondly, this was a very short study, only 4 days for each eating pattern. This is likely not enough time for many of the metabolic adaptations to take place. General practice is about 2 to 4 weeks for fat adaptation, so a longer trial of a few weeks to months may observe different changes or perhaps even more significant ones. However, still very cool to see results in just 4 days. One confounding variable here is the lack of control over dietary intake during the first 2 days of each pattern. We know little about what participants ate during this period, only when. And that's the cool thing about intermittent fasting. But we do know that the macronutrient composition is very, very important, but this just wasn't looked at in the study. Eating ketogenic with less than 5% of your calories from carbohydrate versus eating 50% carbohydrates for calories would have created a very different paradigm in terms of ketone, glucose, and insulin load on the body over the experimental period. Another point I'd like to have seen is whether the people at the end of the 18-hour fasting window started becoming ketogenic. 18 hours is just around the border where I expect ketones to start rising and be present at substantial levels. especially if people were eating a ketogenic diet as they were going into the intermittent fasting window. You know, when I do an 18-6 eating pattern and I'm eating keto, I'll definitely be in ketosis. These comments really go back and target the ultimate question here that all these different types of intermittent fasting studies are really trying to unpack, which is, one, how does fasting work and what's the best way to reap its benefits? Is being in ketosis the main metabolic driver, or is the pause in consumption the main metabolic driver? Or how do these two things actually interplay? This study shows how powerful high unrestricted feeding can be. Even a fasting pattern of just 4 days was able to show improvements in metabolic flexibility and fat oxidation. As I mentioned at the top, there are a myriad of variations of how to do a fast. When to do the fast, the length of the fast, and the macronutrient composition of food when you eat. If I were to speculate on the rank order importance of these 3 levers, my ranking is this. 1, the longer fasting window is most important. 2, the macronutrient composition of the food when you do eat is secondary. And then the timing of the eating window is tertiary. If it works for your day, it may be a good idea to shift the majority of your eating to an earlier phase in the day. But if not, fasting the type of macros you do eat probably captures the majority of the benefits as seen in this particular study. My suspicion is that getting into ketosis is the key important trigger point that sets off much of the metabolic benefit of fasting. Thus, the levers of timing, the length, and the meal macros are just different toggles to control in order to get into periodic ketosis. So the way to really confirm this hypothesis is to, 1, understand the variations of different fasting routines and determine whether they share the underlying same mechanism of action, and then 2, determine whether that mechanism of action is simply becoming ketogenic, and therefore the end state of ketosis is driving the most of the metabolic benefit. Lastly, while in ketosis, does consuming non-insulinogenic calories from fats or ketone esters blunt some of the benefits of fasting or not? There's a lot more research to be done in this space, and when it's published, we'll be here to break down those studies for you. Now it's our turn to hear from you. Have you experimented with fasting and found a particular strategy that works for you? And of course, subscribe to our podcast platform or on YouTube. Until then, keep up the self-experimentation and strive to be the best human you can be. We're here to help you on your journey.